The aircraft no one was supposed to see on April 8, 1941, at precisely 2:35 in the afternoon, an enormous aircraft began moving along the runway at Nakajima's Flight Test Center outside Tokyo. The size of the machine was startling. It stretched well beyond 100 feet from nose to tail, and its wings extended close to 140 feet from tip to tip. No Japanese aircraft had ever approached this scale. As its four engines roared to life, the ground beneath it seemed to vibrate. Officers and engineers from the Imperial Japanese Navy watched silently. Their expressions revealed both pride and unease. This moment had been a long time coming. Nearly 18 months of work had gone into this aircraft. Almost $1 million had been spent acquiring the American airplane that inspired it. A carefully staged lie had been fed to the public to conceal its existence. And now, at last, the aircraft was airborne. As the pilot pushed the throttles forward, the bomber lifted slowly into the humid air. Too slowly. The engine strained audibly. The climb rate was shallow and uncomfortable. Control inputs felt heavy, delayed, almost reluctant to respond. From the very beginning, the aircraft behaved like something burdened by more weight than it could manage. This uneasy first flight was not a surprise to those who truly understood the project. The problems had existed long before the wheels left the ground. Japan had acquired advanced American aviation technology, studied it in minute detail, and attempted to adapt it for military use. The goal was ambitious: a four-engine strategic bomber capable of striking targets across the vast Pacific Ocean. Instead, the result would become one of the most disappointing heavy bombers of the Second World War. This story is not simply about an aircraft. It is about overconfidence, secrecy, and a fatal misunderstanding of how technology truly works. It begins years earlier, far from Japan, during a period when the United States was redefining what air travel could be. America redefines flight by the mid-1930s. Commercial aviation in the United States was advancing at a remarkable pace. Airlines were expanding their networks, aircraft were becoming safer and more comfortable, and passengers were beginning to see air travel as a practical alternative to trains. Manufacturers competed fiercely to design aircraft that could fly farther, carry more people, and operate more reliably. Douglas Aircraft Company stood at the center of this transformation. Its DC-3 airliner had begun to demonstrate what modern commercial aviation could achieve. But even as the DC-3 entered service, airline executives were already thinking ahead. William Patterson, president of United Airlines, approached Douglas with a vision that pushed. What emerged from this effort was designated the DC-4E. It was unlike anything that had flown before. The aircraft introduced tricycle landing gear, allowing it to sit level on the ground. This improved passenger boarding, cargo loading, and ground handling. Its massive wing provided the lift needed for such a heavy aircraft, while four powerful engines promised reliability and safety on long routes. A distinctive triple-tail design kept the aircraft short enough to fit inside existing airport hangars, avoiding costly infrastructure upgrades. Inside, the cabin offered a level of comfort unheard of at the time. Seating was wider and more refined. Sleeper configurations allowed passengers to travel across the continent overnight in real beds. Air conditioning maintained a comfortable environment regardless of outside conditions. Advanced flight controls and electrical systems reduced pilot workload and increased operational capability. On paper, the DC-4E represented the future of air travel. In reality, its story was only just beginning. First flight, high hopes, and hidden cracks. By early summer of 1938, the DC-4E prototype was finally ready to leave the ground. Douglas chose Cloverfield in Santa Monica, California, as the site for its maiden flight. This was familiar territory for the company, home to its primary production facilities and many previous first flights. Still, no aircraft Douglas had ever built carried expectations as heavy as this one. At the controls sat Carl Cover, Douglas's chief test pilot and one of the most respected aviators in the United States. Cover was not simply a skilled flyer, he was deeply woven into the history of American aviation. Born in the 1890s, he had learned to fly during the First World War and later transitioned into test flying at a time when every flight involved real danger. By the time the DC-4E was ready, he had already piloted the first flights of several landmark aircraft that shaped commercial aviation. On the morning of June 7, 1938, Cover approached the DC-4E with the calm discipline that defined his career. He conducted his pre-flight inspection methodically, aware that no checklist could ever be too thorough when flying a prototype of this scale. One by one, the 4 engines were started, each coming to life with a deep, resonant sound unlike smaller aircraft. The airplane, registered as NX-1810, slowly taxied toward the runway as ground crews watched with a mixture of pride and unease. When Cover advanced the throttles, the aircraft began its takeoff roll. It required a long stretch of runway to build the necessary speed. Eventually, with steady pressure on the controls, the massive machine lifted into the California sky. The most advanced commercial airliner ever constructed was airborne. The flight lasted less than an hour and concluded without incident. Cover reported that the aircraft was generally stable and controllable, though not without quirks that would require closer examination. For Douglas engineers, this was a moment of cautious optimism. The airplane flew. That alone was an achievement. But first flights rarely tell the full story. Testing reveals reality. Over the following months, Douglas pilots subjected the DC-4E to extensive testing. Flights explored its handling across a wide range of speeds and altitudes. Engineers evaluated climb performance, cruise efficiency, stall behavior, and system reliability. Every new test revealed data and new concerns. As was common with ambitious designs, several systems failed to perform exactly as intended. Electrical components proved complex and difficult to troubleshoot. Hydraulic systems required careful maintenance. Performance figures began drifting away from early projections. Certification was delayed while issues were addressed. Engineers worked to refine systems, reinforce structures, and adjust operating procedures. Eventually, in May 1939, regulators approved the aircraft for commercial evaluation. That approval marked a turning point. The DC-4E was no longer just an experimental machine. It would now face the realities of airline service. A historic passenger United Airlines took delivery of the prototype for in-service testing. During this period, the aircraft visited several cities for demonstration flights. One stop carried special significance. In June 9, Douglas faces a crisis for Douglas Aircraft Company. The outcome was deeply troubling. Years of effort and millions of dollars had produced an airplane no one wanted to operate. The prototype sat at the factory, a constant reminder of overreach. The consortium airlines paid modest settlement fees, covering only a fraction of the development costs. Douglas absorbed the rest. Company leadership now faced a difficult choice. Scrapping the aircraft would mean accepting a total loss. Yet finding a buyer for such a complex and flawed airplane seemed unlikely. Douglas decided on a two-part strategy. First, engineers would design a new 4-engine airliner based on lessons learned. It would be simpler, lighter, and more practical. Complex systems would be removed. Proven engines would replace experimental ones. The new design would prioritize reliability over ambition. Second, Douglas would quietly attempt to sell the original prototype. That decision would set in motion events no one at the company, or in the U.S. government, fully understood. An unexpected buyer in late 1939, representatives from Japan's Mitsui Trading Company approached Douglas with interest in purchasing the DC-4E. The stated purpose was civilian use by Japan Airlines, which was expanding routes across Asia and the Pacific. From Douglas's perspective, the offer seemed straightforward. Exporting commercial aircraft was legal. There were no obvious red flags. The price, $950,000, offered a chance to recover some losses. What Douglas did not realize was that Japan Airlines was only a cover. The true buyer was the Imperial Japanese Navy. Japan's military leaders had closely followed American aviation developments. They understood that 4-engine aircraft were essential for long-range operations. Yet Japan lacked experience designing machines of this scale. The DC-4E appeared to offer a shortcut. The purchase was approved. The aircraft would leave America quietly. Shipping the secret in September 1939, Douglas workers disassembled the DC-4E at Long Beach, California. Crates were packed carefully, just as they would be for any valued customer. Along with the aircraft itself went an extraordinary collection of documentation, blueprints, test data, performance reports, maintenance manuals, and even wind tunnel models. Douglas technicians accompanied the shipment to Japan to assist with reassembly. At Haneda Airport near Tokyo, they worked side by side with Japanese engineers, explaining procedures and answering questions. To the Americans, this was routine customer support. To the Japanese, it was an education of priceless value. Once assembled, the aircraft appeared briefly in Japan Airlines colors. Photographs were taken. Executives posed beside it. The public was told that the airline's flagship aircraft would soon enter service. It never did. A plane that vanished soon after initial test flights, the DC-4E disappeared from public view. Japanese newspapers reported that the aircraft had crashed into Tokyo Bay shortly after takeoff. The loss, they claimed, was total. No wreckage was recovered. The story was entirely fabricated. In reality, the aircraft had been transferred to Nakajima Aircraft Company under direct naval orders. There, engineers began dismantling it in secrecy. Every component was measured, photographed, weighed, and documented. The fake crash served multiple purposes. It explained the aircraft's absence, discouraged foreign inquiry, and shielded the Navy's secret bomber program. Japan was about to attempt something it had never done before. Behind closed doors at Nakajima's facilities, the dismantled American airliner became the focus of an intense and highly secretive effort. Engineers worked in guarded hangars, documenting every structural element of the DC-4E. Nothing was overlooked. Wing spars were measured down to the smallest tolerance. Control linkages were traced end to end. Wiring paths, hydraulic lines, and fuel systems were carefully mapped. Japan's naval aviation leadership believed they had obtained a technological treasure. This aircraft represented a level of industrial aviation design Japan had never achieved. The expectation was simple: study it closely, reproduce its strengths, and adapt it into a long-range heavy bomber capable of projecting power far beyond Japan's shores. The project was assigned a new designation under Imperial Navy secrecy protocols. Internally, it was known as the Navy Experimental 13 Sure land-based attack aircraft. Later, it would receive the name G5N, with the formal title Shinsan, meaning mountain vibration. To the public, it did not exist at all. From the beginning, Japanese engineers faced a fundamental problem. The DC-4E had been designed as a civilian aircraft. Comfort, redundancy, and safety margins had driven its structure. A bomber, however, required strength under combat conditions, the ability to carry heavy payloads, defensive armament, and long-range fuel capacity, all while remaining fast enough to survive. Transforming one into the other was far more complicated than anticipated. Industrial limits exposed. Nakajima engineers attempted to adapt the DC-4E's airframe to military use, but Japan's industrial base struggled to replicate key aspects of American manufacturing. Aluminum alloys of equivalent strength were difficult to produce consistently. Precision machining on the scale required for such a large aircraft pushed factories beyond their normal capabilities. Where Douglas had relied on advanced stress analysis and extensive testing, Nakajima often had to rely on educated guesses. Reinforcements were added to compensate for uncertainty. Structural members were thickened. Brackets were strengthened. Each change made the aircraft safer on paper, but heavier in reality. The weight problem grew steadily worse. As military equipment was added, the airframe became increasingly burdened. Bomb bays were installed. Crew stations were added. Armor protection was introduced in critical areas. Defensive gun positions were designed into the nose, dorsal, and tail sections. Each addition addressed a requirement, yet collectively they pushed the aircraft far beyond its original design limits. The DC-4E had already been considered overweight in American civilian service. Now, as a bomber, the problem was becoming severe. Engine choices that defined failure. Perhaps the most critical challenge involved propulsion. The American prototype had relied on powerful engines unavailable to Japan in sufficient quantity or reliability. Nakajima substituted domestically produced radial engines rated at approximately 1,800 horsepower. On paper, the numbers appeared acceptable. In practice, the engines struggled under the aircraft's growing mass. Cooling problems emerged almost immediately. Cylinder head temperatures ran high, particularly during takeoff and climb. Oil systems proved unreliable during long flights. Attempts to improve engine performance led to further complications. Modifications altered airflow patterns, creating new cooling imbalances. Engineers found themselves in a cycle of fixes that generated additional problems. Unlike American manufacturers, who could draw on years of large engine experience, Japan was attempting to learn these lessons in real time, on a massive and unforgiving platform. The first prototype takes shape by early 1941. The first G5N prototype was nearing completion. It retained the unmistakable proportions of its American ancestor, a broad wing, 4 engines, and a towering triple vertical tail. Yet its role was entirely different. Painted in naval colors and stripped of civilian markings, the aircraft stood as the largest land-based airplane Japan had ever built. For the Navy, it represented hope, a potential answer to the vast distances of the Pacific. On April 8, 1941, the aircraft was prepared for its maiden flight. The event was carefully controlled. Only essential personnel were present. No press coverage was allowed. The program's secrecy was absolute. As the engine started, observers noted the strain immediately. Exhaust smoke darkened the air. Vibrations ran through the airframe. The aircraft taxied slowly, almost reluctantly, toward the runway. When the pilot advanced the throttles, the G5N began its takeoff roll. Acceleration was sluggish. The aircraft consumed an alarming amount of runway before finally lifting into the air. The flight lasted only a short time. An uncomfortable reality. Reports from the cockpit were deeply concerning. The aircraft was difficult to control, particularly at low speeds. Control surfaces responded slowly. The climb rate was far below expectations. Any loss of engine power would almost certainly be catastrophic. Engine temperatures rose quickly. Pilots were forced to reduce power to prevent damage, further limiting performance. Landing the aircraft required careful planning. These were not problems that could be solved with minor adjustments. Subsequent test flights confirmed the initial impressions. The G5N could barely carry a meaningful bomb load while maintaining acceptable range. Fuel consumption exceeded projections. Maintenance demands were overwhelming. Despite its size and complexity, the aircraft offered little advantage over smaller, more reliable bombers already in service. Redesign without direction. The Navy refused to abandon the project immediately. Too much time and prestige had been invested. Nakajima was ordered to continue development, exploring engine upgrades and structural changes. Engine replacements were tested. Propeller designs were revised. Weight reduction efforts were attempted, though each cut risked structural weakness. None of these efforts produced meaningful improvement. By mid-1942, Japan's strategic situation had changed dramatically. The war in the Pacific demanded aircraft that could be produced quickly, maintained easily, and operated from limited airfields. The G5N met none of these requirements. What had once seemed like a shortcut to advanced technology now appeared as a costly diversion. From bomber to burden, the Imperial Navy quietly reclassified the G5N. It would no longer be pursued as a frontline bomber. Instead, surviving airframes were reassigned as long-range transports, roles that did not require high performance or heavy armament. Even in this reduced role, the aircraft struggled. Engine reliability remained poor. Spare parts were scarce. The aircraft's size made it vulnerable to enemy fighters, and its defensive armament was inadequate for contested airspace. Only a small number were ever completed. None would see combat as bombers. Japan had succeeded in copying the shape of an American aircraft, but not the system of engineering, industry, an experience that made such designs workable. A giant with no purpose by late 1942, the Imperial Japanese Navy had quietly accepted what engineers had known for months. The G5N was not a viable combat aircraft. Its original role as a long-range heavy bomber was officially abandoned, though no public announcement was ever made. The project simply faded from operational planning documents. Rather than scrapping the airframes outright, naval planners attempted to salvage some value from the enormous investment. The remaining G5N aircraft were reassigned to transport duties. In theory, their large fuselages and long range made them suitable for moving personnel, supplies, or high-priority cargo between distant bases. In practice, even this reduced mission proved problematic. The aircraft's engines continued to suffer from overheating and mechanical failures. Maintenance crews reported frequent oil leaks, unreliable magnetos, and excessive vibration. Long-distance flights often ended with unscheduled landings due to engine trouble. The aircraft required constant attention just to remain airworthy. Fuel consumption was another persistent issue. The G5N burned fuel at a rate that made it inefficient compared to smaller transports. In a war where fuel shortages were becoming critical, this alone was enough to limit its usefulness. Too big to protect the G5N's size, once viewed as a symbol of progress, now became a liability. Its large silhouette made it easy to spot, and its sluggish handling left it vulnerable. Unlike dedicated transport aircraft designed with survivability in mind, the G5N lacked adequate defensive armament for contested airspace. Japanese commanders avoided assigning it to routes where Allied fighters might be present. As Allied air superiority expanded across the Pacific, safe operating zones shrank rapidly. The aircraft's potential operating area became increasingly limited. Some airframes were reportedly grounded for extended periods due to lack of spare parts. Others were used sparingly, reserved only for missions where no alternative aircraft could carry the required load. In effect, the G5N became an aircraft that existed, but could rarely be used. Allied intelligence takes notice despite Japanese efforts to keep the project secret. Fragments of information eventually reached Allied intelligence services. Reports of an unusually large four-engine Japanese aircraft began to surface in late 1942 and early 1943. Photographs were scarce, descriptions inconsistent, and official Japanese documentation non-existent. Initial Allied assessments struggled to classify the aircraft. Some analysts believed it was a transport. Others speculated that it represented a new bomber type still under development. Without reliable performance data, conclusions remained tentative. As the war progressed, captured documents and post-mission reports gradually clarified the picture. By 1944, Allied intelligence had identified the aircraft as the G5N, assigning it the reporting name, Liz. The designation carried little urgency. By that time, it was clear the aircraft posed no significant threat. A comparison that told the truth when evaluated alongside Allied heavy bombers such as the B-17 or B-24, the shortcomings of the G5N became impossible to ignore. Those aircraft had benefited from years of iterative development, extensive testing, and powerful industrial support. Their engines, while not flawless, were reliable enough for sustained combat operations. Their airframes balanced strength, performance, and producibility. The G5N had none of these advantages. Its range fell short of expectations. Its bomb load was limited by performance constraints. Its climb rate and ceiling were inadequate for survival against modern interceptors. Production numbers were too small to matter even if the aircraft had been successful. What Japan had acquired from the United States was a physical example of advanced aviation design, but not the ecosystem that made it effective. Lessons learned too late internally. The failure of the G5N forced difficult conversations within Japan's aviation establishment. The belief that foreign technology could be rapidly copied and adapted had proven dangerously optimistic. Without equivalent industrial depth, testing infrastructure, and operational experience, even the most advanced designs could become dead ends. The resources devoted to the G5N might have been better spent refining existing aircraft or accelerating more practical programs. Instead, valuable time and material were consumed by an aircraft that never fulfilled its intended role. As Japan's strategic situation worsened, priorities shifted towards simpler, faster-produced designs. The era of ambitious heavy bomber projects effectively ended. The G5N slipped quietly into obscurity. An aircraft that symbolized miscalculation today, the G5N is remembered not for what it accomplished, but for what it revealed. It stands as a reminder that technology cannot be separated from the systems that support it. Engineering drawings alone do not create success. Experience, manufacturing quality, testing, and logistics matter just as much. Japan had purchased an American airliner that even its creators considered impractical. In attempting to turn it into a weapon of war, the limitations of that decision became painfully clear. Yet the story was not entirely without consequence. The lessons learned from the G5N influenced later Japanese designs, encouraging more realistic performance goals and simpler systems. Even failure, it seemed, could offer instruction. After the war, the truth emerges when the Second World War came to an end. Allied investigators began examining Japanese aviation programs in detail. Factories, airfields, and design offices were inspected, and surviving aircraft were catalogued. Among the many projects uncovered was the little-known G5N. To Western analysts, the aircraft was immediately recognizable. Its proportions, layout, and structural concepts revealed its American origin almost instantly. Investigators traced its lineage back to the DC-4E prototype, confirming what had long been suspected but never proven during the war. Technical evaluations offered no surprises. Reports described the aircraft as excessively heavy, mechanically unreliable, and unsuitable for combat operations. Its engines were judged inadequate for its size, and its performance was far below that of contemporary heavy bombers. In many ways, the post-war assessments echoed the same criticisms American Airlines had made years earlier. The aircraft was not preserved. None survived into museum collections. Like many unsuccessful wartime designs, it disappeared quietly, leaving behind only documents, photographs, and lessons. Why the G5N still matters at first glance, the G5N may seem like a historical footnote, an obscure aircraft that never changed the course of the war. But its story carries deeper significance. The project demonstrated the limits of imitation. Japan had acquired an advanced example of American engineering, yet lacked the industrial framework required to adapt it successfully. Large aircraft demand more than blueprints. They require special materials, refined manufacturing techniques, extensive testing programs, and years of accumulated experience. The G5N also highlighted a broader strategic miscalculation. Long-range heavy bombers were complex, resource-intensive systems. Attempting to develop one during wartime, without a strong foundation, diverted attention and resources from more practical solutions. In contrast, nations that succeeded in heavy bomber development had invested in those capabilities long before the war began. By the time conflict erupted, their designs were mature enough to evolve rather than struggle. A cautionary chapter in aviation history. The journey from American airliner to Japanese bomber was shaped by ambition, secrecy, and misunderstanding. What began as a civilian experiment became a military gamble that failed to pay off. The aircraft that once symbolized the future of flight ended up illustrating the dangers of overconfidence. It showed that technology cannot simply be purchased, copied, or rushed into service. True capability grows slowly, built on experience, infrastructure, and an honest understanding of limitations. Today, the G5N stands as one of the clearest examples of how even the most impressive machines can fail when removed from the environment that made them possible. And stories like this, where innovation collides with reality, are exactly why military aviation history remains so fascinating. If you want to keep exploring the hidden successes, failures, and forgotten projects of the Second World War, make sure you stay connected with WWII Impact. There are many more stories waiting to be uncovered.